I really want to thank Michael for inviting me here today. He only had one real requirement, and that is that I have to have some kind of tech in my background to be able to speak to this audience. So first of all, I want to understand the audience. How many of you work in some federal or state organization? That's a minority. Okay, how many with vendors? Private HPC providers. Okay, what am I missing? Call it out. Commercial providers, private? You're a state organization. Oh, maybe you're a private university. See, I forget that because I'm from the University of Illinois. We did, yes. Okay, so universities. How many at universities? Oh, all right, all right, all right. So my qualification for you in having enough of a tech background is that, actually, let me back up. I earned my education in the form of a CPA and an MBA, and I had to learn how to spell HPC. And I'm going to share with you a little bit about how I learned that and why I learned it today. But in the tech background, I qualify because I took Fortran. But perhaps more importantly, I actually played MIT's adventure game on a luggable compact. And I think that qualifies me to do a command line. Who else played that game? Anybody remember that? Oh man. Okay, got one gray-haired guy up here, and that's it. But before that, I also in college played Star Trek on a teletype with yellow paper. Gosh, no, you don't even know what I'm talking about, do you? You do? Another gray-haired guy remembers. Okay, all right, all right. Gotcha. So, that's my tech background. Anyway, I want to talk about three things. Next slide will show that. Really, the economic development piece. So most of what I worry about every day and what I talk about is why should we care? Why should we care about the tech? Why do I want to care? Why does it need to be better like you suggest it can be? Why do we care? And I often get brought into academic communities to chat with them about why we should care about industry. And we should. And then I'll just share a little bit about accelerating business from our perspective and a bit about addressing the future. Next slide. And then the next one. So this is a little bit about where NCSA lives. NCSA, National Center for Supercomputing Applications. We live on the campus of the University of Illinois. We are a research university. Don't bother thinking about application because we want to prove that we're a fundamental research university. That makes a difference. There are a lot of places out there that are more applied than we are. However, the academics live on the left side of this graph. They do the basic research, and we need a lot of it when it comes to industry and actually pushing science. God bless them. But they don't do a lot of this commercialization over on the far right side of the graph. They don't always get it out. They like to invent things and then stick it in the corner of their room and go invent another one. So innovation doesn't always get the product out the door. NCSA lives in the middle. We're in the applied space. We robustify, if that's a word, these kinds of things, and we do some of the proofs. And we help get these things out. And we have commercialized a few things. And I'll share what some of those things are with you. So this space is rare, all too rare. Where do the most powerful users on Earth go to actually test systems to see if it will work and if it could be commercialized? How do we go? Where do we go to have these conversations? Next slide. Here are just a couple examples so you know where we have lived. Caterpillar, their modeling and simulation folks started and sort of grew up in our facilities at NCSA. Caterpillar is 90 miles away in Illinois, and today their global simulation center is in Champaign in our research park because it started in our facilities. We've got a few others on the list. Motorola, just a fun little thing to understand here. They did simulation. They've probably done it for 20 years on our systems. And a competitor comes in and they're looking at the simulation on a screen and said, well, what fraction of the cell phones in that, because what they're doing is simulating the phones on the tower. They're building out the tower space. What fraction of the cell phones are you simulating with that tower? And the guy says, all of them. What we're probably most famous for is the Mosaic. Now, it's easy to say some kind of a trite comment about Mosaic being an unfunded project, but what it was finding things that were already in existence and pulling them together to make something better. And that was graphical interfaces to what was called the internet back then, and blah, 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 and Mosaic comes out and changes the world. Well, that's what we do, and we didn't want to make a lot of money because we don't want to do that in academia, so we sold it for $1 million. Next slide. Many of you know about HDF. Dan Reed, our director, made Linux the de facto operating system for HPC. He is now serving penance at Microsoft Research. Also, Apache server software came out of our shop about that same time. So we've got a legacy of doing things that actually become commercial in this space. And because we're in this university umbrella, we like to give things away and we don't get beat up. Next slide. Okay, let me talk a little bit about acceleration. Next slide after that. I really like Susie's quote here. This does not say those of us who really think we're cool ought to do a lot of HPC. What it says is an HPC driven solution. What we need are solutions. And it really doesn't matter whether it happens with HPC or not. Next slide. These are my partner companies today. We had a couple spaces on the bottom for some folks who have verbally committed, but we'll have that word out fairly soon. And you'll notice adaptive on here. So we partner with organizations. We partner with companies, not in the academic sense. A lot of you are academics here on the pure academic side of the house, may have an affiliation with the industry, may bring them in occasionally. We want to partner full-on, joint venture, let's get something done. So you'll notice the top of the slide is mostly manufacturers. A couple of them there you may not know, at least one of them you don't, but we have really healthy, behind closed doors conversations with these people, and we learn a lot. Had a Boeing guy come to me one time and said, you know, when we usually go to a university, we talk to ourselves. We shut the door and we're having a conversation about the IP and what we want to do, but when we come to your place at NCSA, my goodness, we get to talk to other people. Oh, that's cool, and very productive and valuable. BP, some others, anyway. Nokia Siemens is the follow-on to Motorola. Pretty special there. Next slide. I just want to give you this background a little bit so you understand the business case as to why we care about industry. These are the Fortune 100 companies, all in with total revenues. So it looks like we have $4 or $5 trillion business sectors. Finance is one. What did I call that other one? Distribution. Actually, $300 billion of that is Walmart. Did you know, by the way? Rich brought it up earlier. Where did he go? He scooted out on me. Anyway, Walmart collects 1 petabyte of data every hour. They can't keep it all. So what do? They come to us. Talking to them in 2 weeks. They worked with us for some time. But the reason manufacturing makes a difference in this space is because they're not as private as Wall Street. They're not led by one company like the distribution, which is Walmart and a lot of those kinds of places. And manufacturing is farther along than many of the other sectors. Oil and gas is pretty far along, but they act like Wall Street. They don't want to share. Manufacturing shares because there's a lot of commercial codes that everybody cares about. And commercial codes run in the HPC environment. So we do care. Next slide. We can achieve high fidelity models on our highfalutin machines, but it takes too long. What industry tells me is it must fit into the design cycle to become relevant tomorrow. So Caterpillar does a fairly well-known model of oil in the differential of a tractor. Yeah, we talk about these things in Illinois. You know, this works for us. they're using Fluent on about 32 cores, and that qualifies as a power user, mind you, and it takes 4 months. If it takes 4 months, that means it's going to be stuck in the HPC corner of R&D in the basement forever. These guys who do this will never see the light of day in the real production line system, because modeling and simulation is typically given 2 weeks. In the entire product, let's build it, life cycle, modeling and simulation is typically given 2 weeks. That means we could speed up. It will stay in the basement. That's the point. Bad way to really do business in a better way. Next slide. I want to chat with you a little bit about how we've had typically 3 federal agencies that can spell HPC. You know them: DOD, DOE, NSF. We found another one: Department of Commerce. This is new to them. The White House actually gets it. We've got a public project called the National Digital Engineering and Manufacturing Consortium, endemic. The guy in the back left, the federal CTO, Anish Chopra, really seems to get it. He's now gone. He was that good. But we were all in a room. We signed the 5-year MOU with a number of organizations. Next slide. This is what endemic does. It is a public-private partnership. There's money in this from 4 companies. There's money in this from the Department of Commerce. It's only $5 million. It won't buy a whole lot, but it will help change the game. It's targeted at the SME community, the small and medium manufacturers specifically in that supply chain. Anish really gets it. I say that this is really cool. We got more than 3 federal agencies that can spell HPC, and that's really good because the Department of Commerce cares about economic development. Chopra says we need all hands on deck, and I'll talk a little about that today. Next slide. So I put together some new data today. I actually had not compiled all this, and coming here gave me a reason to chat about it. So I've got several comments from ISVs here. You know what the ISVs are like. These are the commercial vendors for code, and I've anonymized these. One of these ISVs says they have 3 product groups, and that's all based upon the sales model. But what I find is the smaller firms are pushing the technology and the physics in the code just as much as the big companies, because they build different things. Does Ford build a radiator? No. A supplier does. So the supplier, the radiator supplier, does very different modeling than what they do in Detroit. The ISV also says that their costliest asset is this 24/7 support group. That's because they're dealing with mostly small companies who really, really need help. Inside the companies, and I've learned this, and this is a real aha for me, is that the companies fairly arbitrarily will limit core access. It's a mass market system inside Ford or inside Caterpillar or inside some of these companies, and they've got a limited cluster, so they say, okay, thou shalt access 64 cores and no more, because we've got to spread this around. Well, what do you do for the power user? What do you do for that poor guy who's trying to speed up his 4-month job doing this axle model? He is going to get help internally. One ISV says that 90% of their users are at 8 cores or less. Do we want to call this HPC? Well, we normally wouldn't. But what's being done with the 8 cores? What could be done if that same model could run on more cores? Is this a chicken and an egg syndrome? Whose fault is it? Is it the pricing model that we're not running on more than 8 cores, or 4? Talk more about that later. Next slide. So the OEMs actually talk about a few things that are valuable here. Tom Lang at Procter & Gamble, top quote, says, we don't want to dumb down the product. You know, think toothpaste or something else. We really don't want to dumb down the product, but we also don't want to over-design. They need lots of modeling and simulation to pull that off. There's not enough integration these days. We want some business results here. We want speed up, and we want decrease in costs, those kinds of things. At the bottom, I sort of like what Sam Ellen says. He said that HPC accelerates companies away from all these poor decisions they've been making for years. Poor design. Drive your tractor, John Deere tractor. You know where it breaks. And it will. It may be better than the other lawnmower you might have. But anyway, next slide. Now the little guys, not the ISVs, the user community really cares about a few things. One small company is trying to do a 3D model on, gosh, 1 million elements, and it takes way too long. Another company trying to reduce material with just a 2D CAD model. That's not happening. Most SMEs will build to spec. If you're a supplier to Procter & Gamble, you're going to build to spec because they tell you what to build. So why should they innovate? Can they innovate? Do they have enough know-how to innovate? Well, if they do, P&G's competitor also benefits. Oops, does that work? We're finding right now that there's a big demand for multi-physics among the smaller companies. Think about the radiator. We need thermal, we need CFD, we need all sorts of things. And this is really testing the ISV model. Another important thing is a lot of companies are testing to the spec, and then they quit testing. Think about the physical testing. We don't know how far it'll take to actually break it because we stop the testing. We just test to spec, just like we build to spec. Another very important thing, these machines that are simply too small. Next slide. So we at NCSA decided that if we're going to do things the academic way, and if we're going to sort of ride the tail of NSF machines, which we're allowed to do, we can sell 5% of the NSF machines, but what happens is after a year, the machines are too old, too slow, they got a queue just flooded by a bunch of academics, we may not be able to get on, and we can't serve a community very well that way. If we want to really stay ahead and move the dial for some of the world's biggest power users, we decided we've got to do it a different way. So we built our own cluster. No federal money, no state money. Call it retained earnings if we can do that in the university business, but that's what we did. So we put our own money in. And the reason we did it is because we bought lightning fast cores, and we architected the machine to make Abacus just scream. Now Abacus is the biggest, baddest code we can get our hands on. Some of you will know what the I/O challenges are inside Abacus. They're real. We built it to scream, and it beats every other machine that we can get our hands on. My guy's telling me 5 minutes. Oops. But anyway, we built it because it's a unique resource, and we can show others how a really fast, unique resource can actually change the game. Next slide. We've also found that we need to put all this talent in the room at one time. In order to do that, we can't just run the machine. We have to run it with people who have domain expertise on Abacus, and that means we've got to know the structural materials, and then some and then some. I know in our environment in academia, the computer scientists don't know the domain, and we don't even teach them HPC very well. Oh, we need all three of them in the room at the same time. But you know what? Those three, we might not want to let out of the room and actually talk to industry. So we actually need somebody who can be the consultant in there at the same time. We can bring it all together, and we do regularly. Next slide. Let's skip that one. Next one. I want to get to Blue Waters and some other things. Next slide. All right, Blue Waters. Most of you in this room will know what the bogey is. It's very different than what it has been in the past. I think 9 target applications have to run at a sustained petaflops. Not 1, not 2, 9. Next slide. You pretty much know this. I actually thought the path to yottabytes was going to take forever, but I just heard something about the NSA and some of the things that they're doing with data. Big storage. And also, by the way, the 50 petabyte quote there, what we're building out with Blue Waters is the roadmap to 500 petabytes of data storage. It'll be the world's largest and the world's fastest total, all in. Next slide. This is what the machine looks like. I'm not going to spend much time on specs because I want to get to some provocative statements here after this. We're going to have a petabyte and a half. Look there in the middle. Petabyte and a half of aggregate system memory that we can load things up into like in an hour. Is this a flops machine? What would you do with a petabyte and a half of data that you can actually access all in one system? Don't know what you do, but we'll have some fun finding out. Lots of cores, lots of storage. It's a game changer. Next slide. The Cray CEO says that by 2020, all of Blue Waters will fit into 3 racks. That's rather encouraging. You can just buy a rack and get a lot of business done. And you know the price will come down. But you know what we have to do between now and 2020? We have to tame the beast, and we have to have better software. Next slide. Here's our machine room build out. The top was about 3 weeks ago. The bottom was yesterday. And you can go up to our website, to the ncsA.edu website, click on Blue Waters, and this picture will update every minute. Now, all the way across the room in the back, we'll have an aisle full of all these carrier racks. We're going to have more than 300. 380? Is that what I heard? Something, quite a few. Next slide. And Cray says this, that hey, we're not just in the flops business, we're not just in the data storage business. In order to do data analytics, we're going to do it a lot differently as well, and that's the high end. Next slide. So, these are my predictions. Last slide. If we think about how to build out a digital supply chain, think about the radiator guy giving a digital model to the OEM, having it analyzed, and then sent back to say, build it, or maybe put in a few changes in there. What if we did all this on 100 gig bandwidth in between the supplier and that OEM? What does the supply chain look like today? Oh, the bottle manufacturer that wants to sell something to P&G sticks a train car load full of bottles on a track and sends it over there for them to physically test. You don't want your Tide bottle breaking, so we've got to test the bottles, right? Physically test them. What can we do with the digital supply chain and get rid of the train car? Because the small supplier is pushing capability today, I don't want to call it the missing middle. Stephen Wheat and Intel and the rest of them who talk about that, I think it's a misnomer. What we need is to introduce far more capability into that supply chain. And if we do it for manufacturing, then we can do it for cancer, and then we can do it for biology. We'll start with manufacturing. We've got 2 big national projects today. How many of you know what NMI is? It took me a while to say that fast. Manufacturing innovation. How many of you know what 3D printing is? Any of you have any idea that, well, let me just state, 3D printing is largely the plastics business today, having to add another layer of plastic and so forth. Nobody has achieved 3D printing with metal. Nobody can achieve it with titanium. But that's the demand, that's the wish. Do you think we'll need some modeling and simulation to figure out how to even do 3D printing with metal? I think we will. This really does represent, and I know Dave is going to talk about this a bit tomorrow, it represents a huge computational shift from just academia to the enterprise. To get this done, we in the HPC business cannot stay with HPC as usual, because we deal with the black box, and we really don't ask, nor do we care what the pre-processing challenge is. In the academic community, it might have been somebody's PhD. It took them 10 years to do the pre-processing just so they could get the privilege to go run on a machine for free. It's not the way it works in business. The pre-processing is called CAD or CAE. You have to build a mesh. Who would like to build a mesh for an aircraft carrier? Takes far, far longer than the modeling and simulation. So why don't we in the HPC business figure out how to speed that up? Oh, it runs on one core, mind you. The CAD and CAE business never grew up with parallel programming. So do we have our heads in the sand? Well, I'll put my hand up first. Yeah, we do. We have our head in the sand with HPC because we don't even ask what the on-ramp is like for pre-processing, and we don't care much about the off-ramp, the visualization. There's some people in the room here who actually do that, and we should care more about that. If we're going to move the dial and step up and have things done in the next few years and actually build things safer with higher quality, not just cheaper with less cost. You know what a guy told me the other day? He said, you know, when we build an airplane engine, we can't stick a sensor in the combustor. You have to model it, because there are some things that just simply cannot be physically tested. I'll say a couple other things here and I'll quit. The cloud, Cray says they're going to take the path for high-end computing, and that's not the same path as cloud. What I say is that the user really cares about cloud, so we in the HPC community should care about cloud. It's the access model that needs to change. No single entity has enough money. We need $1 or $2 billion to fix the software problem. And that's the software that we know about today. No company has enough money. No single agency has enough money. Adaptive? How about you?
Almost.
Almost. So we're going to have to joint venture. We're going to have to change our business models. I just scared the bejesus out of Addison here a couple weeks ago by saying that the problem with exascale, you know what, I'm not the technical guy, the problem with exascale is a business model. If we don't solve the business model, we don't get real work done. That's my story, and I'm sticking to it. Thank you.